So folks, we're continuing our discussion of autonomous ODEs. Remember, those are ODEs that look like, for example, dx dt is equal to some function just of x, the dependent variable, meaning the independent variable doesn't show up at all in that. So we're looking at the qualitative ways we could analyze these rather than focusing on the explicit solutions, which we could do. We're looking at the solutions qualitatively, and what's actually pretty cool is we can quickly graph all of the solution curves to this autonomous ODE. So in the process of doing so, the first thing you need to do is, of course, plot the axes. So let's do that. Here is, well, let's see here. Here is my independent axis, which is time in this case, or t, and my dependent axis is, maybe you could think of displacement or whatever, but x is the dependent variable here. Then the next thing you're going to do is you're going to plot the equilibrium solutions. That is the constant solutions, which we found from the critical points. So in our last video, we said, okay, well, we've got these three critical points, x equals 0, x equals 2, x equals 5. Those were the numbers that I could plug into the autonomous ODE, which caused the rate of change to be 0. And of course, once the rate of change is 0, it never changes, right? It can never change beyond that if it's just a first order ODE. So we're going to plot those three critical solutions. So here we have the first one. So this is just the solution x of t is equal to 0. And then let's see here, here's 1, 2, and so here would be the second solution, x of t is equal to 2, and then 3, 4, 5, let's go up just a little bit higher, 6, 7. So then here is our, let me make that line a little bit straighter. There's the critical solution, x of t is equal to 5. Meaning these solution curves, once x achieves the value of 2, if x is the value of 2, it will forever be the value of 2. How come? Because the rate of change when x is 2, the rate of change is always 0. Okay, so those are our three critical solutions. Okay. Then we're going to plot test points. Now these test points only depend upon choosing dependent variables. They're independent of time, right? So let's say we pick, like over here, we pick the test value 1, and we said, hey, if we plug 1 into this differential equation, that's going to spit out a negative value. So we know that when we plug in a 1, it's got to have a negative rate of change, meaning the slope of the tangent line there, that unit tangent line, has to be negative. Likewise, when we plugged in 3, we said it was positive. When we plugged in 6, we said it was negative. And when we plugged in -1, we said it was positive. So I guess I forgot to put -1 there, so let's put that up there. So there is -1, and we said it was positive. Okay. Once you have these, notice that these solutions, for example, never change. And I could sketch that all the way across. It's going to make my diagram really cluttered if I do, but those are the same regardless of the choice of t. Why? Because the rate of change is independent of t. Okay, so now we've got those slopes on there. So the next thing to do is there's only one way to complete the graph. So let me just say careful, because students sometimes don't do this correctly, but there's only one way the graph. And by graph, what I mean is the sketch of solution curves. So we're sketching several solution curves here. So let's take, for example, maybe a solution curve that we'd be passing through here. So if we have a solution curve in this region, it has to be behaving similar to this. Now, let's take this solution curve. I'm just going to go ahead and sketch it, and then we'll talk about it. That's the easiest way to do it. So here's this solution curve right here. Oops, I'm sorry, I've got that backwards, folks. Let's try that again. Oh, no, I had that right. So here's that solution curve right there. Okay. Now notice that this is some solution curve. You could call it, some, it's just some x of t. But look at how it behaves. at this point right here, it has the same slope, just as I have here. And the further I go towards, as time progresses, what has to happen to this curve? Well, since x is increasing, the x-coordinates are getting closer and closer to 2. To 5. As x gets closer and closer to 5, the tangent line becomes closer and closer to this horizontal tangent line that we have. Likewise, if we go back in the other way, we would have been coming from a place where x of t is equal to 2, so it would be something close to that, which means that our tangent lines have to be very, very close to horizontal. So that's one solution curve in this region, and I could go ahead and sketch 2 more. And I could, and careful here, there's a whole field, right, that I'm not sketching all solution curves because that would just make a solid black graph, but there are 3 solution curves in that region. Now over here, it has to do almost the exact same thing, but in the opposite direction. Here are 3 of my solution curves. Let me put one more. Here's a third one. So there are 3 solution curves. Notice I'm putting arrows on here to denote time moving forward, moving to the right. Okay. But notice that for any x value inside of this swath, sitting inside of these 2 red regions that we've graphed, the derivative has to be negative, which means that we always have to have negative tangent lines everywhere inside of this region. But as the x-coordinates get closer and closer to either an x-coordinate of 0 or an x-coordinate of 2, they have to have close to horizontal tangent lines, which means the only shape, you may be wondering about this shape, the only shape that can make this work is that squiggly shape that I've made here. Now be careful. Down here, for this region down here, for x values that are below 0, well, first of all, for any x value below 0, we have to have a positive tangent line. So those solution curves have to have positive slopes, right? And they're not bound, they're not going to be 0 again. So in this case, our solution curves will look something like this. That's the only type of curve that is always increasing, but asymptotically approaches a horizontal tangent line as the x values get closer and closer to 0. Likewise, down here, these have to move this way, and here we've sketched the phase portrait for this particular differential equation. Now, even though we actually haven't, so these would be, several different solution curves given, different initial values. So, each one of these curves that I've drawn in black here is a solution curve to initial value problem. We actually don't know. I didn't tell you what these functions were for each one of these curves, but you know that if I give you, for example, let's just say I give you the initial value problem, so it's for the same dx dt is equal to negative x times x minus 2 times x minus 5, and let's say I tell you that x of 1 is equal to, let's say I tell you x of 1 is equal to 3, you know how the solution curve behaves because you know that the ordered pair 1 comma 3, and I didn't put any t tick markers on here, but maybe there's the ordered pair, maybe there's where t is equal to 1, so that would be the ordered pair 1 comma 3, and so your solution curve needs to behave this way, meaning it has to have asymptotes at x equals 2, and again at x equals 5, it will always be increasing in this S sort of fashion. So even though we haven't found the solution to that curve, we haven't given an explicit description of it, which we would get through solving this ODE right here, we can say quite a lot about the solution, including its long-term behavior. So for example, we could say as t goes to infinity, notice that x of t for this particular initial value problem will be approaching 5. Folks, we're going to do a whole bunch more of this analysis in our next class period, but I just wanted to show that to you so that we're ready to roll with these more challenging questions in class. Thanks for your patience, and I'll see you in class.